these systems are slow, right? Like, when you step back and you think about, well, like, there's no way to make this distributed, decentralized system as fast as NASDAQ and as fast as NYSE. Like, where does the value come from? Why would it ever be competitive? And you actually have to take a step back and try to think about what NYSE and NASDAQ do. They synchronize the world's information. I think a lot of people say they want to infinitely scale blockchains, and they really do think infinity. And that's actually, I think, overestimating demand is as bad as underestimating it.
Solana's core approach is ultimately going back to the beginning, is optimize the network for increasing bandwidth over time, increasing compute with multi-core performance over time. And then later on, if these novel network optimizations arise, like data availability sampling, the network can ultimately add that.
Core value that we want to do is like going back to that. Let's reduce latency, eliminate fees that are caused by bottlenecks, and like really get the fees to be as low as hardware, because everything else is a tax, right? It's sand in the gears of global finance. It's a tax on every consumer. Like, if we eliminate all of that, that's a lot of value that's created for the world.
Put the nail in the coffin. The design is really, the world has latency. It's a big place. You have to ultimately propagate that information to, right now, historically, New York. Ultimately, in Solana's end state, there will be multiple leaders today, kind of similar to like AWS. They kind of have geographically located data centers in different parts of the world. You can send your transaction to that closer leader, and by that time, hopefully you'll already be in the block and that arbitrage will not exist. Effectively trying to create a more synchronized world system than you would if you just have to send all your information to one entity in New York.
That's basically it.
Well, Toly, thank you so much. Round two. Honestly, the last podcast that we did, it was one of my favorites. Deep diving turbine, sea level, kind of talking about multiple leaders, bandwidth, and it's been a year since we did the last podcast in person. And I wanted to touch upon some of the things that I feel like you tweet a lot about, but are still not either fully appreciated, or you kind of get to insert them into some podcasts but don't get a deep dive. So I want to kind of center this around some of the more technical things that you talk about that I don't feel like are fully appreciated. The first one, I think, is the all-to-all synchronization. You touch upon this, and specifically, I feel like the best podcasts that you've done are, or I've seen you communicate around the Modular Summit. But maybe just to kick off this podcast, can we like deep dive all-to-all and sharding and zero-knowledge proofs and L2s, and why specifically you focus on all-to-all communication?
Oh, for sure. This is kind of like the foundation of how I got started with Solana. So like I know there's like this myth of Vitalik playing World of Warcraft and then having the rules change on him, and him feeling rugged by the World of Warcraft team. And that's what inspired building trust minimized computation, right? This idea that you have a computer that cannot be modified, that everyone knows the rules of. Well, prior to starting Solana, I was, an engineer, worked most of my career at Qualcomm. I was also a hobbyist trader. Like, I wasn't any good per se,
Yeah.
But like I loved the idea of like trying to parse a lot of data, build like algorithms and things like that. It like forced me to learn about deep learning and all sorts of other analysis, and like kind of just worked well within my like kind of signal analysis brain. That's, I think every embedded systems engineer ends up working on some kind of signal analysis. So like it was fun, but what I noticed is whenever I thought I had an edge, my trades would arrive later than I expected, and then the information that I needed would take too long to sync.
Yeah.
So it felt like there was like something in this black box that was like against me. So when I got the idea for Solana, just like, I can build a really fast blockchain, like what is it good for? My immediate thought was like these systems are really, really good for finance. They have this guarantee that there's a way for me to submit data in a guaranteed way, and it takes at least a third of the network to block that, to like start reordering data. And also being part of the network, I have a guarantee of receiving the data as well in a timely fashion. So like, again, these guarantees, you have to bound them within a certain number of milliseconds and stuff like that.
Yeah.
But if you like architect the system correctly, it takes a very large number of the network to be collaborating in a corrupt way for you to like receive the data later, or for you to not be able to submit it in a timely fashion. And that was like, I thought was really, really cool, because what we end up with is a system that is run by volunteers. It's effectively open hardware. It might be expensive, or to some people, or to me, like $350 a month for a box somewhere is not expensive. It's very affordable. Me as a hobbyist trader would have gladly paid for that. Like when the cost in comparison at like NASDAQ or NYSE are like tens of millions of dollars per year, right? So like this is effectively free for that use case. So like if my only cost is the hardware, and I get these real-time guarantees that I can submit, and I have a guarantee in submitting that information, and I receive the data, it's a really, really awesome value creation for the world. And then the question becomes, well, like, these systems are slow, right? Like, when you step back and you think about, well, like, there's no way to make this distributed, decentralized system as fast as NASDAQ and as fast as NYSE.
Yep.
Like, where does the value come from? Why would it ever be competitive? And you actually have to take a step back and try to think about what NYSE and NASDAQ do. They synchronize the world's information. There's kind of this, like, a bunch of data. It's kind of in this high entropy state. Nobody knows what the actual offer or on any given asset is around the world. And there's news events that constantly occur. And all this data rushes from around the world, right? From Singapore, from Japan, from everywhere there's markets and people like do stuff. It's rushing into a single location in New York. And it's all being ordered and synthesized as fast as possible. Well, like, the global information latency is actually the same.
Yeah.
It still has to propagate. That news event has to go from Singapore all the way to New York before a trader can look at it and then compare, does this news actually impact the market or not? So when you think about it from that, there's actually kind of this like minimum latency around the world for all this stuff to synchronize, and Solana can be as fast as that. So like in comparison, you're not going to get 1 millisecond kind of trading on Solana, but what you're going to see is that a news event happens in Singapore, that in that market, somebody could, as soon as they see that news, submit a transaction to Solana, and it starts propagating and get it into a block producer immediately as that news event goes all the way to NYSE. So by the time a trader at the New York Stock Exchange sees that news event on Bloomberg, they're going to look at a price on Solana and a price at NASDAQ or NYSE. It's going to be exactly the same. And that means there's no like arbitrage of like real news value trading between this decentralized system run on open source software by a bunch of volunteers on like relatively cheap hardware and something that's very expensive and like very much kind of an insider's club to get into. That's really, really cool, right? It means we kind of like cracked open this like very, very hard problem. And that thing, right, for that to function, it just from sharding is just not a thing that would make it better. It would actually create two different synchronized states that now have arbitrage between them. So actually sharding doesn't help, rollups don't help. None of the stuff actually helps solve that problem. So this is why in our design and everything that we built, we've always thought we have to figure out how we like crack open this idea of information synchronicity or like reducing entropy around the world, however you want to think about it, and be competitive with NYSE and NASDAQ. And that just leaves these other technologies kind of off the table. Like sharding's not going to help you. Zero knowledge proofs don't really help. All this stuff becomes secondary, like priority. So this is how we've attacked the problem. And it turns out if you build a system for like super high performance all-to-all messaging, you actually get very, very good utilization of the hardware, and that's what drives the fees down. And this is something that's very counterintuitive to a lot of other builders in crypto.
I think that's a beautiful setup. Yeah. There's a lot of things I want to dive into quite a bit. Maybe the first thing is, I think the ability to actually add a box and like actually plug into the network. And as you mentioned, historically with NYSE or NASDAQ, I mean, they literally give everybody the same cable length, so no one has a slight edge. And here, and please correct me, you're giving everybody the ability, or the Solana Labs team has ultimately built the ability for anybody to connect a node to the network and effectively receive information almost in real time as everybody else in the network. And I think that is the big breakthrough, allowing anybody with relatively cheap hardware compared to kind of traditional standards to gain access to that information.
Yeah, that's basically the idea. And I think, my dream is that this becomes like the backbone of global finance in the distant future. Like everything runs on Solana, and like even NASDAQ and NYSE then run on top of Solana. That's going to take a lot of work. And
that would be wild.
Yeah, but like 20 years is a short and long time.
Yeah.
It's a short time in like human time frames, but in computing time frame, it's 1,000x in performance on every parameter.
Yeah. Maybe touching upon like going slightly deeper into like the entropy, and particularly around, as you mentioned, a news event happens in Singapore, it goes to New York, that is transmitted through some fiber optic cable around the world, ultimately ends up in New York, and that trade happens. And I think, as you mentioned, I mean, these decentralized systems, when you start to replicate different nodes, they're always, I mean, you're going to have some real-time latency that you're just not going to be able to ultimately be one-for-one with a more centralized system. And so maybe can you double-click a little bit further on kind of how you view these all-to-all communication channels, and really versus like a single entity running it, and reducing the arbitrage by effectively already having that price in by the time it hits New York.
Yeah, so you have like in a system like traditional centralized system, you have an exchange in New York, and all the trades from all the brokers and all these UIs, like from Fidelity, etc., they kind of go through a bunch of hops and end up at the exchange eventually. And news also gets aggregated as close to co-located to these systems as possible. It also goes through kind of a web, but you kind of want to be like, you have your algorithms in a machine that's really close to the New York Stock Exchange, and you're feeding it news triggers after they've been processed to go like adjust whatever markets and algorithms people want to do. So for us to be competitive, the event, if it occurs in Singapore, there should be a short path to a block producer that's closest to Singapore that doesn't have to go all the way to like New York and then back out around the world. And the way to achieve that is that Solana right now runs with a single leader per slot. So there's a single leader that's randomly selected globally. You can actually have 10 leaders or 20 or whatever, however many you want. We'll start with 2 first, but like basically you have 2 block producers. So now you've cut your geographical latency on average by 50%. When you have 4 block producers, it's now 25%, 25% distance and so forth. So you can kind of like, it's almost like Starlink. I don't know if you've ever seen those maps of Starlink. Yep. There's right now 1 satellite that's spinning around the world, and the likelihood that you're next to it is pretty low. But you can keep doubling the number of those satellites to the point where there's basically like 1 millisecond or 5 millisecond path. And like as that number shrinks, the arbitrage that you can get between NYSE and Solana shrinks and shrinks.
Interesting.
And I think that actually there's going to be a flip much closer than like 5 to 10%, because you still have all of this latency of sending all this information to the New York Stock Exchange and processing it along the way.
So, and just to kind of like put the nail in the coffin, the design is really ultimately, the world has latency. It's a big place. You have to ultimately propagate that information to, right now, historically, New York. Ultimately, in Solana's end state, there will be multiple leaders today, kind of similar to like AWS. They kind of have geographically located data centers in different parts of the world. You can send your transaction to that closer leader, and by that time, hopefully you'll already be in the clock or in the block, and that arbitrage will not exist. Effectively trying to create a more synchronized world system than you would if you just have to send all your information to one entity in New York.
That's basically it. And there's going to be like a bit of slicing, right? So maybe it's 100 milliseconds or 150 milliseconds. That's the slice of the block. And within that block, you may have to have some periodization and bid for it. But you're going to approach really, really closely to like the time value economically of that prioritizing within that block for the world. And I don't think you can get like cheaper than that.
Yeah.
And this is like, I think the really cool thing is that like the cost, I think of finance as like a regressive tax. It doesn't itself create any value, right? Like every time you pay, like do a transfer and there's a few bips here, a few bips there, it's like people charging to move numbers around a computer. And like there's got to be some minimum price to it. And like I think the fastest synchronized global state machine that like lets you synchronize as much state as possible with the lowest latency, it's going to have the lowest amount of tax on the world. So this is kind of like what we want to get to, that like smallest time slice that we can have around the world for everyone to send their data to and have the minimum amount of priority that they're paying over time and like have that stuff resolved. And I think that's like, the best financial rails for the world with the least amount of value extraction. It's the one that should win over the long term and like benefit the world the most, right? Like within 100 years, you imagine like what does finance looks like? It has to run on something like this. Like it has to run on the cheapest, fastest rails possible. Otherwise, we're like kind of wasting, GDP growth. We're like wasting human resources.
It's a beautiful vision. I'm definitely looking forward to that day. Kind of staying on the topic of the all-to-all communication, I mean, you talk a lot about whether sharding, different architecture designs, layer 2s, whether fraud or validity proofs, zero knowledge proofs. Those ultimately do not solve this kind of global synchronization problem. They ultimately isolate state, and I think maybe kind of visualizing it's kind of going back to that New York model.
Yep.
You're sending all your data to a single entity that's in one part of the world. Can you maybe just dive slightly deeper for the listeners and kind of compare and contrast why all-to-all should be focused on versus kind of these different methods that...
Yeah, so the reason why you need all-to-all is because we want to guarantee that if you're a participant in the system, that you receive the information as fast as possible too. And you can't guarantee this in every possible way, but what we can do is that because of how data is propagated to all the machines at the same time and they all collaborate retransmitting it, it requires a certain percentage of the network to be malicious and try to withhold that information for that process to slow down. And that percentage is roughly like a third, like 1/3 of the network has to be Byzantine. So, in like BFT terms. So that means that we can have some guarantees looking at the Nakamoto coefficient that if there's enough participants that are all independent, it's very unlikely for all of them to be malicious. And then we can, if they are, we can detect that and slash them and do all sorts of stuff. It kind of makes it robust from that point of view. Mm-hmm. And for that to work, right, for that time synchronization, like speed to work, you have to propagate the data to everyone. As soon as you shard that or start doing tricks like that to reduce the cost, right, the hardware resource cost in the network to do that, you're effectively letting some part of the network get the data first. That means that they get to see the information first and they can be the first to trade and kind of extract value from the system that way. And this is like what I really, really want to avoid, because I want to be the hobbyist that's like, oh, I have a very clever algorithm. 10 years ago, I was messing around with deep learning. Maybe I was first to do that, right? And there's no way I could have won even if I had an innovation, because I was just getting beaten on the physical access by all the big boys. So that's really, I think, the problem that I want to fix and make sure that it's impossible for the big guys to extract value that way.
Interesting. And to kind of double click on that, I mean, some people say you can have all to all within a single L2 in terms of having going from a single sequencer to multiple sequencer, but the end state would look similar to Solana.
Yeah,
correct?
but that's just saying that Solana could be an L2 of Ethereum if Ethereum has enough data availability
I want to get
bandwidth.
into this later, but
and Ethereum could be an L2 to Solana. The L2 thing is just a bridge. That's all it is. People should stop thinking of it anything else but a bridge.
I do want to get up to L2s, but let me first. One thing that you also mentioned earlier on was kind of amortizing the costs of bandwidth to all nodes in the party.
Yep.
And I think this is actually really fascinating in what you ultimately communicate is that like being able to get the transaction costs to facilitate this on-chain trading or whatever it may be as close to bandwidth as possible. I think we'll kind of skip the like core bandwidth part because we touched upon that in the last podcast. But can you touch upon, how you kind of amortize the costs of like the bandwidth to all nodes?
Yeah, so like the way that sharding and all these other systems work is that they basically say it's too hard to propagate a lot of bandwidth in any given system. So we're going to limit a subcommittee to, let's say, 100 nodes or 200 nodes. And each one will maybe do like 1 to 2 megabytes per second. And then they confirm and then send that data to the rest of the network and the beacon chain. Or like there's effectively some design where there's a single thing called the beacon chain that coordinates a bunch of subcommittees that all sync data. And each subcommittee has limited bandwidth. So the problem there is that you have a small channel, right, like with 1 or 2 megabytes of capacity. And the way that fee pricing works is that your fees should be effectively based on the remaining capacity in the channel. And it kind of can stay pretty low up until it hits 100%, and then it's going to spike to a very high amount. You can think of it almost like when the Suez Canal was blocked by a single ship, right? The cost to get goods through that canal it became very, very high because there was very limited bandwidth now. And if you had a bunch of, like, if the Suez Canal was smaller and was like 100 small capacity channels, the problem would be even worse because you have one ship that could block the channel. For that channel, the price goes up and you kind of have to reroute to other channels. So ideally, you actually have a channel that is so big that it never hits that capacity limits because you've aggregated capacity across all your channels. And there's tricks to do that when you have a bunch of small capacity channels, but it becomes harder. You're kind of introducing delays and synchronization. And I kind of wrote this out in a tweet. Like, imagine Solana was an Ethereum L2. What would that look like? Solana at 10 gigabits would require like 600 subcommittees on Ethereum. That means that for every second, Solana is bidding on 600 subcommittees on Ethereum to include Solana data, different data, right? And like all 600 have to accept without reordering. And if there's a reorder, Solana then has to go and like make sure that block gets retried, and you probably see that happening once a second. And so like, go ahead.
I'm just going to try to, it makes sense to me, but I want to summarize it. Today, the ultimate bottleneck in these blockchains is blocks, or how big the blocks can be. And because that blocks your data, you have to propagate the blocks to all the nodes in the network. Today, Ethereum has relatively small blocks. With 4844, they're introducing slightly more data. And with these committees for dank sharding, it's going to be like 1.3 megabytes per second. In Solana's, they're much bigger blocks. They're much faster. Firedancer is working on a client that I think is 10 gigabit are a target, and 1.3 megabytes per second versus gigabytes is totally different. So as Anatoly was explaining, ultimately you're going to need 600-ish Ethereum bandwidth channels to just be able to settle for Solana, ultimately making prices much more expensive. Correct?
You kind of like think of it as like there's capacity, right, in the network. Like just think of it as like, Suez Canal, right, shipping. If you have a lot of small channels, like one big boat is going to clog up a single channel.
So you're clogging all the multiple channels because you're exceeding all the bandwidth for every one.
And the pricing in that channel for that specific channel is going to shoot up.
I see.
And then you have to reroute to a cheaper channel if you logically can.
Yeah.
And to build the systems that can reroute logically, that pushes complexity up to the top of the stack, and that will delay finality, because now you have to deal with channels that could reorder potentially and things like that. You have to synchronize all of them, make sure all of them get synchronized, and that's more complex versus you have one giant Suez Canal that's so big that it never fills up. That means that you're never going to run an auction that runs out of space.
And can you talk about, so obviously to get more and more bandwidth, kind of the key places to do that is like data centers. So they historically have had the highest bandwidth and the lowest costs. I think Latitude provides like 64 cents per terabyte of egress, which is pretty crazy. Can you talk about just that raw data costs versus like home validators as well?
Yeah, so like basically bandwidth prices drop roughly like 2 to 3 years by 50%. And it's called the Nielsen's law. And there's a lot of pressure to do that simply because people want to do more FaceTime or more high video content. Now like more AR and VR content is coming online, and that's even more bandwidth intensive. And it's just kind of like never ending process, right? Like,
does bandwidth also double as it drops? Like the cost?
Yeah.
Okay.
So it takes a little longer. There's like a new standard every decade. The 1 gigabit standard is 23 years old at this point. It was defined in 99.
Okay.
The 10 gigabit is 10 years old, I think. So roughly every 10 years, at least, a 10x, there's like a new standard that rolls out. The next one that they're working on is a 400 gigabit standard, right? Like I think that's basically been defined as well. But this is something that just massive industry behind it, trillions of dollars of like infra spend and engineering and R&D that's happening. And like, why is it cheaper to have these large nodes that can manage the system, even though they're all talking to each other, right? It seems expensive, is because of the kind of pricing that you see out of data centers, and that effectively translates into home pricing as well. Just maybe like an order 2 to 3x higher, is that when you're charging like even $1 per terabyte, and you have 10,000 nodes, each one of those nodes has to transmit all the data that it receives out. So every node is doing 10 gigabits or 1 gigabit worth of work. The price per byte is 10,000 times, right? Times $1 divided by 1 terabyte times the overhead that you have in a system like Turbine. It's about 4x. It comes out to something like 4 times 10 to the minus $8 per byte. So it's very, very cheap.
Which is only slightly more than the pure egress cost itself.
It's
like 4x.
It's 10,000 times bigger.
Okay.
Well, like 40,000 times bigger than like the cost
for the system overall, but for the individual validator.
For each individual validator, they're paying just their ingress cost. Yeah. But because there's 10,000 validators and there's like 4x overhead, you can think of it to the user. This network is going to be 40,000 times more expensive than my normal connection sending it into AWS. And that sounds massively expensive. But when you actually run the numbers, it's 4 times 10 to the minus $8 per byte.
Yeah, and bytes are very small.
Right. But bytes are very, very cheap. A single transaction is roughly 256 bytes on Solana, maybe sometimes more expensive. But you can think of it as like the costs per byte on Solana, right? Like when you submit a message is very, very negligible. 10 to the minus 8, even times 1 kilobyte, you're talking like 0.0000 like 5 cents per message. And that is much, much higher than if you were like had to pay that for every FaceTime call. If you had to pay that, that would be expensive. Like, because you're transmitting a lot of data peer to peer. But for something like a network that like a decentralized peer-to-peer network for finance, it's very, very cheap. It like becomes a negligible cost to finance. And this to me is what finance should cost. It should cost the cost of the hardware, maybe with some multiple for all the hardware providers to make a decent revenue. But even with like a 4x multiple on top of that, it's still effectively free. And subcommittees cannot achieve that, like, because we're not seeing the same pricing coming out of subcommittees, even though if you think about it, the numbers should actually work out better in their favor, because they have fewer nodes, right? So that multiple shouldn't be 10,000 times, it should be like 200 times. Because they're limiting bandwidth to the point that those channels get saturated, they hit that inflection point where you start having to auction the bandwidth to the highest bidder, and that causes people to overbid, not based on the raw cost of the materials, but overbid based on the person's need to submit the data, like based on their economic cost. And that's a tax. That's like effectively you're now taxing finance at a premium that's much, much larger than the hardware cost. And this is like why, 4 years or 3 years, whatever, since Solana launched, and we've seen layer 2s and all these other networks launch, they've not been able, like none of them have been able to get their transaction costs anywhere near as close as Solana. And like this is going to be true next year, and this is going to be true the year after that.
There's so many things that we are going to dive into. I want to say quickly just on the channel utilization. I mean, so all-to-all communication is brutal on votes, or coming to a consensus. Probably one of the least efficient kind of consensus algorithms. Other blockchain architectures have come forward with different type of consensus designs, probabilistic, whether a DAG versus kind of a single leader. Can you talk a little bit just about like probabilistic architecture and maybe relate that back to channel utilization?
Yeah, so there's other approaches that people have tried, and these you can think of it as like leaderless, and think of a network with a bunch of different nodes, like 1,000 or 100 nodes, whatever, and each node has 1 gigabit worth of bandwidth. So each one can do 1 gigabit up and down. If you don't have a dedicated leader and the bandwidth isn't allocated to them, like to a dedicated channel, you can have 2 nodes at the same time, because they can't all know exactly what everyone else is doing, start submitting 1 gigabit worth of data at the same time. So now, because the rest of the network is all limited 1 gigabit up and down, at some point somewhere, someone's going to see 2 gigabits worth of information in, and that's going to saturate them. And this is the point where that network is going to break, and then we'll have to propagate information back saying, hey, I'm saturated, I need you to back off, and you need to reconcile that difference and like effectively deal with that collision. And that collision is effectively noise in the channel. If you think of the network as having 1 gigabit worth of bandwidth, as soon as it crosses that limit, that capacity limit, it's no longer able to transmit information globally. So it's in a noisy state. It's effectively like you have way too much noise to signal, and you're not, like Shannon's law applies there. You start dropping bits. So very, very simple analogy, but very much like Shannon law is very, very much applies here. And you can think of this in like radio, same problem. Like the first radio protocols that people have built, like one of the first was called Aloha. You have a bunch of towers, they randomly transmit, and if there's a collision, they have to back off in some random interval, and there's more complicated algorithms to decide how to back off. But they have to back off because if 2 transmit at the same time, you overwhelm the channel with the amount of data that you're sending, and nobody can decode what bits are being transmitted. And that's exactly the same thing. And there's a limit to how many concurrent leaders how many concurrent transmitters can participate in that network, and that utilization of that channel drops at a pretty significant speed. It's almost exponential. I forgot what the number is, but as soon as you start crossing 100, 200 participants in those networks, you have a very, very fast drop off.
And just to re-articulate, I mean, the main thing ultimately is because, I mean, in Solana with proof of history, you have a dedicated leader that knows.
So like the first, when people started building cellular networks and they're dealing with many different transmitters, right? Their cellular network means every phone can transmit, and you're dealing with tens of thousands of subscribers per tower. you're going to have a lot of collisions. A lot of people are going to start transmitting at the same time. So the way that they've dealt with this is called time division multiple access, where you have your frequency that you can divide, but then you also have your time slot, and you assign each phone a specific time slot when they can transmit over a specific frequency channel. And because they're the only ones that can do that, they don't run into a collision and information can propagate through. And this is something that's been done, probably since the 50s, right? Like if you look, but like it's a very, very old idea, a very old protocol, and it works, right? It actually prevents these collisions from happening, and that fundamentally passes more information through the system. So the idea with proof of history was like, the reason why I started building Solana was that when I had the idea for proof of history, I had a very high level idea that there's a way to synchronize time in a permissionless way globally without trying to build a clock synchronization protocol that's permissionless, that deals with adversarial, like people submitting invalid timestamps and stuff like this. I don't know if it's possible to even do that, but it's hard. Like it's even hard to do that when you're dealing with in a network like Verizon, like when just systems are not even malicious, that just go out of whack from power failures or component failures and stuff like this. It's a big pain in the butt to build those systems. So it would have taken as much work to build that clock synchronization protocol as it would have built to the entire network. Yeah. So when I had the high level idea that proof of history is a way for us to clutch together this way to force people to take a specific time slot without having to build this protocol, that was oh, okay, it's going to be much, much easier to build the rest of the network, and we can utilize all the bandwidth available to the nodes because there's no collisions, and the system can be very, very efficient. So that was kind of the kick that I had, oh, okay, I know I can build effectively something that's going to look like TDMA. We're not going to have any collisions between block producers, and I think we can be very, very efficient.
It is fascinating. I mean, ultimately, to take a step back, there's kind of the leader design that Solana architecture has chosen. There's different architectures that DAGs or leaderless designs, but in those leaderless designs, when you have multiple parties ultimately sending large transactions to the network has to kind of come to a consensus. There's only a certain amount of channel capacity and bandwidth, and that causes the network to be
it has to back off and deal with consensus.
Okay.
Right? So
it has to come to agreement.
Yeah, it has to deal with the fork that occurred. So in a very, very simple, the simplest protocol is Bitcoin, right?
Yep.
So the reason why Bitcoin is 10-minute blocks is because if you shrink the block time to 400 milliseconds, you're going to have two different block producers that solve the puzzle at the same time around the world before they saw each other's blocks.
Before they come to a consensus with the rest of...
before they know of each other, right?
Okay.
So that block has to propagate from block producer A to block producer B, and B will switch, its fork, but that doesn't happen. So now you have two head pointers to two different forks that are proposed in the network, and those have to resolve. And that means that your amount of information that you're transmitting is dropped by 50%. Mm-hmm. So if two block producers solve the puzzle at the same time, you've now cut your channel capacity by 50%. If three do, it's by a third, right? So you kind of have this the lower the block time or the lower the difficulty, you have more concurrent forks that you have to deal with, the lower the actual effective channel capacity.
Interesting. So ultimately, when I talk with DAG consensus experts, they all kind of tout whether it's probabilistic or they're able to increase throughput by a 2x or a 5x with this leaderless design. And because they've chosen that DAG architecture, because it is leaderless, ultimately the more parties within that network that are trying to broadcast, that will effectively at scale reduce the ability for bandwidth to be utilized to its full capacity. ultimately kind of making some of those benefits and consists or whatever less performant than if you would have had it a leader and kind of do proof of history.
Exactly, and it kind of like it's counterintuitive. You know, every node on Solana submits a vote for every block, so you can think of it as like thousands of votes. So if you try to optimize that away, like Avalanche, I think, and Snowflake are really brilliant protocols that reduce the number of consensus messages in the network. So imagine we spent all our engineering time and we reduced the votes from 4,000 to 400 per second. That seems like a huge win, right, in capacity. In reality, what we should have been spending our time on is doubling our capacity, going from like 10,000 messages per second to 20,000. Because that gain, right, like just working on very, very like old school optimizations, figuring out where we can use twice as many cores, looking at like flame graphs and like doing benchmarking, that gain gets us from extra capacity, goes from 5,000 to 15,000 versus we get like 5,000 more. So you simply just like get more out of like sitting on the exponential growth curve of hardware than you do out of anything else. And that doesn't mean that you can't apply those optimizations later or whatever. It's just that the way that hardware like expands is just really, really fast. Like it's just 2 years may seem like a long amount of time, but it takes a long time to build the software. It takes a year to go and do these optimizations and prove them out and do all this work. And that's effectively like you're halfway into your hardware upgrade cycle. It's just like not worth your time, because as the hardware improves exponentially, that difference between 4,000 messages per second or 400 messages per second gets smaller and smaller as it becomes a smaller and smaller chunk of your overall capacity. And it just becomes irrelevant. Like, okay, we optimize this one little piece and it has like 5% difference on the remaining capacity. Like, who cares?
So today, a lot of different teams, because the all-to-all communication is pretty brutal, have really optimized consensus around lowering votes. But over the long term, with this all-to-all communication, by increasing bandwidth, you have more allocations for either increased decentralization or increased TPS for application engineers to build novel applications on the network. And Solana's whole point of view is, even though today the votes take up the majority of the bandwidth over the network,
they don't take up the majority of the capacity. They take up the majority of the current use, because there's a very large number of validators in Solana, right? It's half of Ethereum. And even though Solana does more application transactions than all of Ethereum and all its L2s combined, it's just still like 400 or something like that per second.
And eventually, I mean, when you increase more bandwidth, when you increase more compute, if nodes stay the same on the network, you would have increased capacity for transactions. And so instead of saying today there's 5,000 votes, we need to make that 500, you just increase the raw resources of bandwidth and compute, and the network has more.
Within 2 years, Latitude is going to offer twice as many cores for $300, right? And the pricing is going to drop from 64 cents per terabyte to 32 cents per terabyte. So like, why bother working on this like kind of optimization that's very much a very small constant factor improvement, when I'd rather have, you know, all the engineers figure out how do we make sure that when the number of cores double, that we just naturally scale elastically to take advantage of them.
At what point in time do you think, like, ultimately it's up to, I mean, going back to like the all-to-all communication, one of the like very interesting things of Solana was being able to contribute a node to the network. As you contribute more nodes to the network, the communication overhead does increase. Do you think at some point in time, like, the network is going to have to choose, like, hey, like, we should stop node production at like 10,000 or like 20,000 just so we have more room for applications? Or is it just the fact that bandwidth and compute are going to continue to increase over time and you can just scale both?
I'd be really surprised if we run into that limit. I think it's possible, but you can definitely then just have, like, do the work. We haven't done this, but like you can have 2 computers per validator.
I see.
Like it takes, like, Firedance is actually set up really well for this. So once Firedancer's out, their design is very much scalable across 2 different machines. You can
So like enter validator
Yeah.
sharding.
It's just like we haven't done that work. It's just really, really unlikely to need it because
Okay.
like you can get away with like double, like two socket systems. Like you
Yeah.
4 socket systems are rare and like there's not as much benefit to them, but like 2 socket systems are pretty easy. The thing is that like when you look at like crypto, Bitcoin's peak market cap was like what, 2 trillion or something like that. There were about 12,000 computers securing that. My guess is that that's kind of like the upper bound of what you need to provide very, very, 15 nines of guaranteed security across the world. That it's very virtually impossible to go and break all 12,000 systems and corrupt their state. Because you only need one with the correct state to continue. So like at a certain point, just the amount of shared security that the system has created is so large that like you're seeing very, very small marginal benefits going from 15,000 to 100,000 nodes. So like, yeah,
I mean, it makes sense to me.
So like that's kind of like, once we hit that, like, Solana has massive product market fit, everyone's adding nodes, it gets to like that 12,000 point, you probably don't need more block producers than that, right?
Yeah.
Like it's very unlikely that people are going to want to even run a block producer because of services like Jito and things like that start aggregating block producer services and like give you access to these high level features that are programmable. Like you kind of see that just normally occurring in the markets.
I think like in general, it still like confuses me, but there is a lot of misinformation or just lack of education. I think it's definitely, since we did the podcast last year, amazing in terms of like community and what kind of fighting the good fight and misinformation. But I mean, yeah, to your point, Bitcoin had like approximately 12,000 full nodes. Ethereum has about half that, 6,000, and Solana's right behind that with like 3,000. It is very impressive just how many actual full nodes there are kind of syncing all this state globally.
And like my belief is that it's very much product market fit driven. That's kind of the leading thing. And like the nodes spin up because people want to use the state and want to get access to the state. And like folks like Magic Eden, they want to have the best UX. So they want real-time access to the state with as many guarantees as they can. So when somebody does a trade, that NFT pops up as fast as possible in their UI and people have that like snappy feeling, right? Like all that stuff is really driven by like real businesses having demand on like, I want this data as fast as possible. And to them, the hardware costs are like negligible. Like
it is interesting. I mean, you look at like just like cost per cost. I mean, with Ethereum, it's not like Ethereum has 10x more the nodes just because they reduce cost by 10x.
Yep.
I mean, to your point, like if it is valuable to run a node, people find a way to run a node. It's not typically just cost for the sake of cost.
Yeah, you start really like getting very little marginal benefit cutting the cost below that. And this is why a lot of Ethereum nodes run on like cloud and AWS, because even though like that basically like puts like AWS Ethereum nodes pretty close to what it costs to run a Solana bare metal node. That's kind of funny.
Because the egress is so expensive?
Because egress is so expensive and you're dealing with like cloud provider costs.
Yeah.
You're kind of like, okay, like it's at that marginal price where people would rather pay for the convenience of running stuff on cloud versus like figuring out with like the friction of running stuff bare metal.
Yeah.
But like those are like at that point micro optimizations.
Interesting. Maybe next topic that I kind of wanted to touch, and I think we've kind of have on a high level, is really kind of there's 2 schools of camp on scaling data availability. One is kind of increasing I think everybody actually agrees that you have to increase throughput. It's just like, do you do sharding on the data availability layer? Do you add some data availability sampling? Do you keep it all integrated? Do you do volitions? It's just kind of moving around. You can't eliminate it. I think everybody agrees that it has to be done, but the two primary school camps, or at least like schools of thought that I hear talked about frequently, is kind of the Solana approach, and more so recently the eigenlayer approach. Can you kind of touch on maybe the differences between the two, and again, like how eigenlayer is perhaps approaching it versus like the Solana camp?
Eigenlayer as in like the restaking approach.
Correct.
To provide security for Ethereum.
Well, they're going to do data availability sampling. I've actually asked Sharam a lot to like post a paper. They haven't done it as of yet. They're going to I think it's do like polynomial commitments for data chunks, but ultimately they don't reassemble those data chunks. Can you
So all that stuff is fine. Like, I think those are optimizations that just want to provide some security, whether like economic through restaking to Ethereum, or like through sampling. You have like guarantees that if you see these many samples and you're not eclipsed by an attacker that has like perfect network knowledge, that the data is probably available. So you can have like a light client that can confirm that specific data availability subcommittee hasn't withheld data. I think all those approaches increase the security of the system to some degree. The question is, like, for that real-time trading use case, you need the data to propagate globally.
So it goes back to the all-to-all.
Like, and that also provides the same guarantees. Now, it may be cheaper to provide good enough security guarantees with these other approaches, but they don't satisfy this. I need this data in real time as fast as possible. I need it globally available to everyone that's a subscriber. Now you can, like, if you have that like all-to-all subcommittee that's already built, you can add actually data availability sampling on top, and you can do all these other things for light clients that may want to just have better security guarantees on the network. But all those protocols, they're kind of doing what already happens just through informal side channels. If the majority of Solana nodes become corrupted and withhold data, all the other nodes, even if they're not staked, RPC nodes, etc., that see that data withheld, they're going to fall behind. Their pager duty is going to go off. Those engineers are going to go online. They're going to talk through side channels that are very hard to block, right? You may be able to block things on the network layer, but you can't really block the social layer, right? There's just too many ways that people start communicating, and flags are going to go off. Circle is going to freeze their mint and burns. Binance is going to freeze deposits, etc. Right? You're going to see these cascading effects, and that may take hours to resolve. But that actually is what happens in these networks. This is why they're so robust. That it doesn't matter if you control 100% of the stake. That stake itself is a very small part of the network. All the other services that are running on top that are monitoring the network constantly, all those other full nodes are effectively also part of the security of the system, and they provide really strong signals to users whether the network is healthy or not. And light clients are really cool because for some of the failures, you can automatically detect that the network is withholding data and trying to propose invalid blocks. And in a short amount of time span, that's reasonable to like maybe a minute or something like that, a light client has guarantees that they've probably sampled enough nodes and waited long enough that if there is a fault, that it had that time to propagate to that light client. And those are all awesome and can be built on top of Solana. And there's work in the community like Tiny Dancer to add those. But fundamentally, those are optimizations over the kind of security that already happens, right? As any single full node, can go and say, hey, holy shit, the network just finalized an invalid block, and here's the snapshot in the ledger, and it'll take 5 minutes for anybody to go download that and verify and see, oh wow, something happened. We gotta like stop everything.
Yeah. So Solana's core approach is ultimately going back to the beginning, is optimize the network for increasing bandwidth over time, increasing compute with multi-core performance over time. And then later on, if these novel network optimizations arise, like data availability sampling, the network can ultimately add that. And it's not necessarily unique. It doesn't totally provide performance benefits. It could provide kind of security benefits, but ultimately scaling the network with bandwidth, with compute, and then later optimizing or adding in these optimizations can be done.
Yeah, yep. Because the core value that we want to do is like going back to that, let's reduce latency, eliminate fees that are caused by bottlenecks, and like really get the fees to be as low as hardware, because everything else is a tax, right? It's sand in the gears of global finance. It's a tax on every consumer. Like if we eliminate all of that, that's a lot of value that's created for the world.
Interesting. Very interesting. Okay. Well, moving on slightly, I feel like you've been turning up the dial in terms of L2s or bridges, checkpointing. I think some of your tweets that have done fairly well really talk about fees. And I think when the L2 conversation really begun, it was not just kind of moving execution from the base layer to an L2, it was also the fee reductions. Can you talk more in depth specifically around the fees component of layer 2s versus having them like all integrated in a chain like Solana?
So there's two things that cause fees. One is the channel, like the overall capacity of the network drops. And this is kind of like there's a big ship that gets stuck in Suez Canal kind of problem. So like the amount of throughput that the network can do drops. And when you think about like layer 2s and where they help is that you have compute limits. You have a single thread on Ethereum that's got to run through all the smart contracts. And what L2s help is that they skip that part. There's no single thread that's limited by a certain amount of time and resources that needs to execute all the smart contract calls. Mm-hmm. It just looks at the only thing that an L2 posts is like, here's a chunk of data, a bunch of transactions that happen, and maybe a state route. And all it's doing is recording on chain. And there's maybe a zero knowledge proof that comes in later that validates it, or an optimistic fraud proof that challenges it. But effectively, all it does is post data. So that single thread in the Ethereum L1 that's got to look through all the smart contract calls just says, data's there, next, right? That becomes a very, very fast operation. So you've increased the capacity of how many of these calls you can do there. So that's no longer the bottleneck. In an L2, you then have, depending on the design, you have a sequencer, then you have batching that tries to batch all those. All those things have some amount of capacity that they can do. And if any one of these queues gets filled up, you've effectively, like, the system is full, right? There's a ship that's stuck in the canal, and people, the only way to get to the front of the queue is people are going to increase fees and bid to be first. And this means that you have now multiple use cases that all have some value to be first. They don't know about anyone else's bids, and they all rush in and maximize their bids just because now your effective block throughput has dropped. You're only letting a very small amount of transactions through, and like there's way too much demand for that amount of like capacity that you have in the system. And that can happen like in any one of these queues. So as soon as one of these queues is saturated, fees go up, everyone bids to be first or to be included in the queue as fast as possible. And that creates those like kind of fee spikes. But even if all the queues had infinite capacity, the reason why fees may go up is because you still have economic value that's in the state. And like you can think of that as like an NFT mint or a liquidation in a DeFi protocol, or like effectively an offer for something. Hey, I'm selling X for Y dollars. Somebody sees that that's worth Y plus $1, right? And everyone in the world, because this is a public chain, sees that that's worth Y plus $1. So that means everyone's going to bid at least $1 extra, right, to be first to take that offer. And that kind of like fee spike, you can't avoid. It's just that's kind of like a nature of the hotspot problem. You have a single chunk of state that has certain amount of economic value to the world. Mm-hmm. People should bid up to that economic value. And what you really, really want to have is a system that doesn't get saturated by everyone bidding to get access to that first, to be first for that particular state. You want to allow that state to be resolved, and then another piece of state to be resolved at the same time for a different price. And this is what we built with like localized fee markets. And there's no reason why L2s can't do this, but then they kind of effectively have to start rebuilding a ton of the work that Solana has done.
Okay.
You got to have parallelism in the execution engine that like figures out how do we asynchronously compute the state root. You have to then have isolation in the way transactions are submitted. They have to specify, each transaction has to specify which part of the state it's touching and how much it's bidding to be first. And all the queues that lead up to that, like from the users being able to submit this data to like the batching service, the state root computation, all this stuff needs to be able to like manage this parallelism.
So let's dive into it. So breaking that apart, you kind of, the first scenario where like the sequential running those operations, very similar to the Ethereum virtual machine design today. Everything, there's no parallelism. Everything is operated one after another. If you have infinite resources with kind of like the L1 and L2, the fees ultimately arise because of, at some point during that kind of handoff of operation, a channel gets saturated.
Yep.
That could lead to fee spikes. The second one being state contention. So in the Ethereum virtual machine, because it is single threaded, you can't isolate specific contracts on the blockchain. You have the NFT mint that's going. You want to do a DeFi swap, but the NFT mint is making all the fees for everybody much higher. And because it's not parallel, you can't isolate those specific points on the network. Once you enable parallelism, it doesn't necessarily enable.
So like the block producers are economically incentivized to sort everything by priority and then take the highest 100 transactions or whatever it takes to fill up the block without looking at the state. They just care about like what's the highest price. And because they're kind of taking blindly off the top of the heap, if there's a mint and 1,000 people bid $1 to be first in the mint, my liquidation has to outbid all the mints, right? My payment has to outbid all the mints and liquidations, right? So now you get into this gas war that quickly forces like everything to be at its maximum economic price.
And so the kind of modular point of view, at least today, is, I mean, kind of keep with Ethereum virtual machine just for backwards compatibility, but have multiple layer 2s that can kind of, it still doesn't remove like.
Right, so you have to have an L2 that only does payments.
Yeah.
And an L2 that only does liquidations, right? Like, but even there, you're kind of it's really hard to deal with it because as soon as you have 2 NFT mints or 2 liquidations for different markets that occur at the same time, you now have a gas floor that forces everyone to bid up to their the maximum amount of economic value that they can extract. And that's problematic. Like you really like, as soon as the system can do like services more than 2 states at the same time that are independent of each other, you're going to run into this contention. So like this is just a old school database hotspot problem, and the only way to deal with it is with isolation. You have to put each one of these states into their own isolated locks,
which comes from parallelism.
Right, and they're kind of related. To implement parallelism, you have to implement isolation, more or less. There's other ways to implement parallelism, but the way that Solana implemented parallelism is by implementing isolation.
Interesting.
Yeah.
And I mean, the single-threaded EVM is ultimately trying to solve this by multiple different layer 2s, but ultimately you still run into a lot of the similar issues that existed on Ethereum 1 with global fee markets instead of isolated fee markets, particularly because of this state contention issue. And then once you add parallelism, you have
once you add isolation, you also add parallelism because it's trivial to implement parallelism with isolation.
Okay. And so once you have isolation, it's kind of a question of why do you need multiple different execution environments and different layer 2s, and your whole point has always been you should integrate them.
If you integrate everything and you have one aggregated channel, you're you're aggregating all the capacity. So then that point where you hit 100% capacity and fees spike for everyone in this like asymmetric way is further and further away.
Yeah, interesting. One chatting point that I hear often is around modularity in terms of creating different virtual machines. And today it's so early kind of in all these life cycles of the ecosystems, we shouldn't be as opinionated on what the virtual machine is. We should allow the engineers to customize their virtual machines, whether it's single threaded, whether it's parallel, and give them that opportunity to experiment with that. What are your kind of general thoughts around?
Well, like I think there's you definitely want experimentation, especially at the front end language layer. At the back end machine layer, the way that I see it is like, is it good enough? Is if we can support multiple different front ends. And the way that I think that's been demonstrating that Solana as VM is good enough is that you have things like Neon, which is literally EVM re-implemented as a Solana smart contract that can run on Solana in the Solana runtime. You have Solang, which is a front end to the LLVM compiler that's used to generate Solana programs, that's used as Solidity. There's a project to implement Move. And those are forcing us to update the runtime and ABI to be more expressive, to make it easier first to build these front ends and to make it easier for even Solana programs to interact between each other. So like those optimizations are not like, they're very impactful. They like have a lot of impact on developer experience and things like that, but they don't fundamentally change the kind of the high level runtime design where you have transactions that have to specify state that's isolated, and then you do all the parallelism on top of that.
So more opinionatedness on the front end via the programming language gives developers more flexibility, but by having kind of the fastest, cheapest execution environment, that's going to be able to solve like 99% of the use cases on the back end.
Yep. There's like, like there's some reason to want to say like, hey, you guys are using Berkeley packet filter and we want to use WASM. And some developers will want to go build WASM stack, but that level of like differentiation is like not, it's just very preference and subjective. Yeah. It doesn't actually like solve like a business economic problem where you're like, you as a user, you really don't care whether the backend is running WASM or Berkeley packet filter. Yeah. Like it's just so far like differentiate, like so far removed from the user and very much up to developers' preferences. It's nice to be able to say, oh, we serve every possible bytecode and everything else, but it's not an optimization that's like worth creating like a much like sacrificing all the other features. We could actually add loaders that load different runtimes and stuff like that, but that's going to increase the audit cost because now we have to audit WASM stack and all this other thing. It just like becomes a kitchen sink. I'd rather.
Yeah. The other kind of like main like discussion point that I often hear is like the internet is primarily asynchronous versus like synchronous, and that it would be difficult to, I guess, kind of scale past like ultimately the size of one node, and that there should be different environments. Can you also kind of like touch upon that point of view?
There's this is also I think a lot of people say they want to infinitely scale blockchains, and they really do think infinity. And that's actually, I think, overestimating demand is as bad as underestimating it. Like Google serves, I think, about 100,000 queries per second, like searches per second. There's just some fundamental limits to how much any service needs to provide. And if like the Google engineers were told we need infinite number of searches, they would have wasted a lot of their time building something that is, solving problems that they don't really have, right? When you know that you need to serve, 100,000 steady state and 1 million peak, you can build the fastest possible system that fits within those bounds. And that means that you get, you go from 200 millisecond response time to 50 millisecond response time. And that is actually more valuable to the customers. So like from my perspective, my guess, like we're at 400 user transactions per second, and that's more than Ethereum and all its L2s combined. I really, really doubt that within 20 years we're going to see like more than 100,000 transactions per second. Like the top 99.9999 valuable transactions in the world are going to fit in the first 100,000 TPS.
And those are like actual user transactions.
Yeah. Like I just don't see it breaking past that. And to support that, we probably need 10x peak capacity, so 1 million TPS, and that fits in a 10 gigabit network that's available in every data center today, available in like a bunch of homes already. Yeah. Like if we build a system that works really, really well within those bounds and is as fast as possible, like I think it'll actually saturate all of the world's needs.
Pretty wild.
Yeah.
Yeah. It makes a lot of sense. Maybe just sticking on the kind of ZK-L2 briefly and then going to asynchronous execution, because I'm fascinated by that as well. I mean, and just so it's like very clear, it's kind of your point of view, these different L2s are different execution environments. They're not actually scaling solutions, because
they scale in the sense that they remove the single-threaded bottleneck that's in Ethereum.
Yes.
So the EVM itself and the layer one doesn't have to execute those, and it's kind of punting off the execution to these other environments. And it's almost like using a Unix fork to create threads. Like you create these other processes that can run independently of each other, but they're still syncing data to this one single-threaded environment.
And so by kind of sharding that execution, you're giving similar benefits as you would if you were just integrating that with multiple cores. But for a layer 2 specifically, I mean, I guess you can scale compute more, but it's ultimately still going to be bottlenecked by the data availability layer, because you have to ultimately come to consensus with the layer 1.
Yep, you still have to submit your data to Ethereum, so you're as fast as Ethereum will allow you to submit your data.
So you're going back, like you're always bottlenecked by the bandwidth. You can kind of move that to like a Volition or wherever else, but it can't be eliminated, and that's going to be the core
Volition breaks the security guarantees that like what people want at a layer 2. So
yeah,
you still
that's
have
a whole other thing.
Yeah.
Yeah, I agree. Interesting. Okay, I just want to make that super clear. Asynchronous execution. This is something that I see you tweeting about a lot, but I would love to learn more, and I'm sure the world would love to learn more.
This is like an optimization that would allow Solana validators to skip executing all the user transactions and just vote on forks. So imagine the validators, the only thing that they process are votes. So they're only looking at votes, they're only computing the fork weight and picking the next fork. And that means that all the smart contracts don't get executed right away. They can, but they don't have to. So that means some nodes that are like Magic Eden nodes that are serving user data, they're going to want to execute all the user transactions right away. And as soon as they know that the network has confirmed this block, they know that everyone else is going to compute the exact same result, because that sequence of events is finalized, and even if it's parallel, like the actual execution is deterministic, even if it's parallel. So they can compute that state and serve it to the users right away, and they know it's confirmed. They know exactly what that state is going to be. So validators are not bottlenecked by the execution. That the question there is like, what benefit does it provide? Well, it's really, really hard to have the runtime guarantee the exact execution timing on every event. It's kind of a coarse measurement. So on average, we can actually do a pretty good job trying to get every block within 400 milliseconds, but there's sometimes spikes. And those spikes are, bugs. You can think of them as bugs, and they're always getting fixed and always getting better. But what would be better is if the network just could allow execution to slow down a bit and then catch up. And that actually opens up execution to like a really, really cool optimization. If you have like 1 million transactions and you know exactly what they are, you can actually perfectly prefetch all the state from disk and make sure that it's in memory before you actually hit the execution on it. So you never take any cache faults. You can load up all the transactions for the same program on like GPUs if that's possible. You can do all sorts of tricks for batch execution, and even in like the zero knowledge singularity world, where you need like 1 million transactions to go send to this magic massively parallel prover, you can then do that and just submit the ZK proof for the state. So like all this does is it lets validators to like say, okay, I'm gonna vote on this fork. I know what all the client transactions are, but I'm gonna execute them sometime later. And they need to be able to agree to execute all the state some way, like once an epoch, and that's roughly every 2 days. Might shrink to be as fast as every 4 hours, but like kind of basically that over that one kind of giant chunk of time, go execute all the transactions at the same time.
And this is ultimately, allows you to also deal with kind of like these like big batch spikes as well, that you can kind of like amortize the transaction execution over the epoch.
The big benefit that I can see is that if once we want to add multiple leaders to the system, we run into a similar problem that any multi-leader system does, is how do you split bandwidth? Like if you want to split it in a very coarse way, you give everyone 50%, you're probably going to underutilize the network. So what's kind of cool is that you can actually let those leaders to temporarily exceed their bandwidth. There's a spike, and then you start lowering capacity to average it out over like a period of 30 minutes.
I see.
So that would actually smooth out like the capacity and probably give us much, much closer to full utilization with multiple leaders without having this course. Like if you have 2 leaders, each one gets 50%. If you have 4, each one gets 25%. You can actually let them kind of spike up and down.
Interesting. It is fascinating. So I guess like, is there any downside or like trade-offs by like, instead of doing like the state transitions like almost in real time as they come to the block leader or after they come to consensus?
This is like this is one of those optimizations with no trade-offs. It's great.
Interesting.
It's like with no downsides. Like nodes that need the data right away can provision themselves with more hardware to like be able to do it in real time. But validators that are voting on forks really don't need to do that, and then can just run in this like single kind of like batch optimized configuration, and there's like no trade-offs. It's great. Except for the hard engineering that needs to be done to test this to make sure it's bulletproof.
Interesting. Well, I think that was majority of things that I wanted to talk about. Any updates on Firedancer, how that's like progressing?
Go look at their GitHub. Yeah, they're cranking out. I'm hoping that by Breakpoint that there is a Firedancer Frankendancer client,
that'd be cool,
which is running part Firedancer code, part Solana core code. Mm-hmm. I'm pretty sure they'll get there. Obviously no guarantees. These are like engineering timelines are like the worst things to predict.
How many story points is that?
Yeah. But go look at we need prediction markets for engineering timelines. But go follow their GitHub. They're making really, really good progress. And like as soon as they have a runtime that can verify Solana Ledger concurrently with Solana code, I will like sleep twice as good at night.
Have multiple different clients and less worries about any downtime or issues. Yeah, awesome. Well, is there anything particular that you want to touch upon or share with the community?
There's a hackathon that's just been announced called Hyperdrive. I hope all the folks that are listening to this podcast tell their friends about it and go. Literally, these are like the best ways to get into the space.
I agree.
A lot of the founders that have raised real money, real seed funding, they did a hackathon. It was just their first one. It didn't work out, but it sparked an idea that they worked on for like 3 to 4 months and submitted in the second hackathon that was like at that high quality level and like uniqueness that like got them funding before the hackathon was over. So this is like a path for a lot of first time founders. If you're an engineer, if you're like working at a FANG and you're bored in the weekends, like
come to the dark side of
yeah,
crypto.
go build a prototype for Hyperdrive. It'll fail, but it'll give you everything that you need to go succeed the next time.
Amazing. Well, Anatoly, thank you so much again. These are some of my most fond and fun conversations, kind of like nerding out on the different execution environments, how you propagate data. And I really just wanted to make this like super clear, dive into some of the things that you've been talking about on Twitter and give you a little bit more of a long form conversation to dive deeper into them. But truly thank you, and really appreciative of you and what you built here at Solana.
Awesome. Thank you for having me.
Thank you.